My name is Elektra Wagenrath, and I am involved with the development of the OLSR daemon. My talk will handle internals of OLSR daemon by olsr.org. I hope you're interested in so much internal stuff and where the development is currently turning to. I've taken a shot of GraphViz of the Berlin mesh as the background of that slideshow. Hope you can see it. Well, olsr.org started as a master thesis of Andreas Tønnesen, a student at Uppsala University. He implemented RFC 3626 OLSR that was issued by the INRIA Research and Development Organization in France. Our work is currently based on the primary work that Andreas Tønnesen did, but we made lots and lots of changes. We kicked many stuff out of the OLSR daemon that was in the RFC. You still can enable compatibility to the old RFC, but I think there is no reason to choose it. Well, this lecture is not so much of the kind I'm going to introduce into mesh networking in general, just a few basic information. The idea is to have a ubiquitous network that is an infrastructure made by the people that want to consume and use the network. The idea is to use the 802.11 ad hoc mode, the mode where the cards can directly speak to each other and there's no hierarchy. If routing is applied, we can potentially cover large areas because every node acts as a relay and improves the range. I think this will be clear with the next slides. What we want to do is not possible in managed mode. At least it is not possible in managed mode if you only have one interface in your mesh box. I have to admit that in the Berlin mesh, we are now using mesh routers that run links in infrastructure mode because we have several issues with ad hoc mode. The major issue is that drivers are implemented very sloppily because everybody buys cards when at least the infrastructure mode works to some degree. And many manufacturers, firmwares fail miserably in ad hoc mode. And of course, if you want to have a high bandwidth backbone infrastructure, meshing is not the ideal solution for it because if you only have one interface with every repeating process, the available bandwidth goes down because you have to repeat it all the time. In fact, if you use an access point not just as a resource for connecting to the World Wide Web or to a file server that is connected via the Ethernet to the access point, you have significant loss in speed if clients of the access point speak to each other. On that slide, if A and B communicate, well, the access point is quite fortunate, located in the middle, so it can extend the range of those wireless cards. Imagine the range of each card is 300 meters, and after 300 meters, in the middle between A and B, there is an access point. So there's a distance of 300 meters from A to the access point and B to the access point. They can speak to each other, which would not be possible otherwise. But imagine you have two laptops on the same table and you want to share some files, and the distance between D and B, imagine they are on the same table. The distance is 1 meter, but the distance to the access points is 300 meters. Well, you can be lucky if you have 20 kilobytes per second, especially here on the Congress. Compared to that, if you switch to ad hoc mode, you have the full speed, what your cards can have. C is out of the range of the access point. It would be in range of D or B, but they cannot speak to each other because in infrastructure mode, C needs contact to the access point. It's not necessary for the ad hoc mode, and I hope I stressed that out successfully. So in 802.11 ad hoc mode, the nodes can talk directly. This is decentralized, better scalable if the driver works, if the cards work. We have some really bad experience with that. And routing is applied because, well, in that slide, D is out of the range of A, so if B doesn't route, well, they cannot speak to each other, but we're here, or I'm here to talk about routing and mesh networks. Well, what we do, or what OLSR does, it is basically a proactive link state routing protocol. That means every node maintains a database of routes of every other node in the mesh. Here is how this routing table is generated. In the early beginning, imagine you just started the OLSR daemon on node A and B, C, and D. A starts issuing hello messages, which are heard by B. B is issuing hello messages, which are heard by A. So A and B learn that they exist and that they have a link to each other, which is symmetric because they can speak in both directions. Once the nodes learned about the situation or the topology of their neighborhood, they start flooding the mesh with topology information. Well, A says, I can see B, B says, I see A, C, D, and so on. Well, basically, the basic proactive routing protocol, it just floods those topology information regardless if somebody has already heard it or not, all over the whole mesh. I think there's not much to say to this slide. Okay, this is the path of a topology control message and the repeated transmission of it. Of course, if you have a mesh with many nodes that have many neighbors, there's a lot of redundancy in this. Everybody starts repeating topology control messages and they get repeated several times. Of course, this consumes some bandwidth, and the academic approach of the research in ad hoc routing is the academics, they think first about optimizing the bandwidth consumption, and we will further on see how OLSR was intended to solve this problem and what we learned, what it isn't. Well, with the gained topology control information that is collected from each and every node, there is a table maintained, where everybody knows, okay, there's a link between C and A via B and so on, and so every node can calculate a routing table how every node in the mesh could be connected to. Usually these routing protocols, they search for the shortest path to route the package. So now, finally, we come from the generic proactive routing protocol to OLSR. It is a RFC draft, like I said before, 3626, issued by INRIA France. It's proactive using the Dijkstra algorithm that I just described. The communication works with UDP packages. They are broadcasted. Multiple messages can be contained in one UDP packet, and the messages are discarded if the validity time is exceeded and the validity time is told in the UDP package. Basically, what the O in OLSR stands for is those new ideas that were meant to improve this proactive routing approach. The integration of hysteresis and so-called multi-point relays. Let's handle the multi-point relays first. you see there is a node in the middle, and it has several neighbors. And the idea of multi-point relays is to reduce the redundancy of repeated topology control messages. So a node decides it only uses several neighbors, not all, only a subset of neighbors, and tells the neighbors to forward its topology control messages. And others that are not told to be a multi-point relay, they don't forward hello message, topology control messages. And it learns this from hello messages. Well, our experience, we first tested OLSR on the Wizard of Oz at 2003. It doesn't work. We switched this feature off. It was one of the major features that were introduced in OLSR. We found several issues in this new idea of proactive routing. It adds a new and, in my opinion, unnecessary message class and is telling who is a multi-point relay or not. It's still like the previous routing protocol that we tested, like it was mobile mesh. It optimizes routes for the lowest hop count. It tends to find the shortest path, which is not fortunate, and I will explain this later on. The worst thing that made our work completely or mostly useless with OLSR in the beginning was that it has a so-called hysteresis. If 3 hello packages from a neighbor are lost, then the neighbor is kicked out of the routing table. That's very unfortunate if this node that was kicked was a multi-point relay before that was supposed to forward your topology control messages. So the node ended up without having a multi-point relay and without having a link to a neighbor. This happens binary, and yeah, it's just on and off. I have a neighbor, I don't have a neighbor. And what we were seeing and experiencing was we had a routing table that was very long. It broke down, it rebuilt it, it broke down, it rebuilt it all the time. This nice idea, or in theory, on the first sight, nice idea of multi-point relays, it reduces topology information redundancy. Well, it's what it was meant for, to reduce the redundancy and save overhead. But it also reduced the stability in the network, because once you have traffic in your mesh network, you have collisions. And so some packages don't come through, and so you're quite happy if you have some redundancy. And last but not least, every node floods the whole network with topology control messages. Imagine you have a network with 200 nodes, and you say every 5 seconds, every node broadcasts its topology control messages. So every few milliseconds, there is another flood issued by some random node in the network. And what I disliked most was that OLSR breaks the KISS attitude. Yeah, the routing table broke down all the time. It seemed to prefer routes with the shortest path, the lowest possible bandwidth, and no stability. And routing loops occurred more often than not. So the lessons that we learned on Wizard of Oz 2003 was a mesh is a boiling kettle with interference and collisions, especially the mesh that we used because we had only one channel. We were transmitting on channel 10, so everybody is using the same resource, and there are lots of collisions. There are hidden nodes, exposed nodes. And if you need 10 dB signal-to-noise ratio to have a successful transmission with 2 megabit, well, a node that is far out of range still adds some 2 or 3 dBs noise to the noise floor you already